So before I forget, this week is a B Day Friday. So that means this is our only class because this is a Wednesday Monday. I'm calling it a Wednesday Monday because it's Wednesday, but it's really Monday. It's the first day of the week for us. So it's a Wednesday Monday. Tomorrow's going to be a Thursday Wednesday, and then a Friday Friday. So we'll take the Friday Friday. But welcome to Wednesday Monday. This is our only A day because the next 2 days are both B days. So those folks will have all the classes on those 2 days. So this is sometime we meet. So get your pencil and paper out. Get ready for some practice. Get ready for some notes. Got some good stuff we're covering here today. Let's throw something up on the screen to look at. All right, let's go to our grade screen as usual. Look at our grade screen. We are done with the first 2 modules. The test was due this past week. That was last week is the test part 1 and part 2. So hopefully you got that in. Feel comfortable, feel good about what you got. And ready to move into solving quadratics. So we got a whole module talking about quadratics and different stuff. And the funny thing is we're going to start out talking about things that are other than quadratics as well. So greatest common factors, special products, and then factoring by grouping is what we're looking at this week, these first 2 lessons. Okay, let's go. I closed module 2 because we're done with that. Opened up the module 3 folder. Here's the first 2 lessons that we're going to look at, greatest common factors and special products, and all the fun that goes along with that. Oh, Taylor's at it again. She's trying to reframe a square photo using a square frame, but before reframing it, she needs to find the dimensions of the photo. Said she could get a tape measure, but she thought she'd use the exercise to study for a math test, so her dad told her the area is equal to x squared plus 12x plus 36, where x represents the side length of each side of the photo since it's square. She needs to know how much longer each side of the frame is than each side of the photo, so she knows how much matting to use around there, the blank space. All right, we're going to learn how can a greatest common factor be separated in an expression, what methods can be used to rewrite square trinomials, and difference of squares binomials as separate factors, and in what conditions can a factored expression be factored even further. Okay, when we were first learning how to simplify fractions years and years ago, back in elementary school, we learned about finding the greatest common factor, which we also called the GCF, right? That is defined as an integer or variable multiplied by other integers or variables that creates a resulting product. A factor times a factor is a product. So if you were to simplify the fraction 8 over 24, we would need to find the largest integer that goes in, that can divide into both 8 and to 24 without a remainder or a decimal, right? And that one's not bad because 8 and 24, 8 goes into both of those. See, so we can take 8 over 24 and divide it by 8 over 8. Then it becomes 1/3. So that's not bad. That's a nice easy one because 8 actually goes into both of those. But we're going to talk about the same type of thing with polynomials. So I'm going to put this video on the screen. We'll go ahead and check out this video to start us out of class and what we're going to be looking at starting out today.
Ignoring the variables for a moment and looking at each term separately, ask yourself, what is the GCF of 3, 27, and 15? There are at least 2 ways to determine whether or not a group of numbers shares a GCF. You may make a list. Or you may create a factor tree. The factor tree factors any composite number into its unique product of prime numbers. Notice that 1 is not included on the factor tree. The greatest factor that all 3 lists and all 3 factor trees have in common is 3. Therefore, a 3 should be factored out of each term. Write the GCF of 3 in front of the trinomial, then divide each term by it. It is not necessary to show the 1 in front of w to the 4th power, since it is understood. Now take a look at the variables in each term. Do the terms have any w's in common? It may help you to see any common variables if they are shown in expanded form. Since the last term is a constant, there isn't a variable that is common among all terms, so the greatest common factor, GCF, must simply be 3. The final factored expression is 3 times the quantity w to the 4th power plus 9w squared plus 5. Be sure to check the factors by distributing the GCF. The factors work because their product is the original polynomial. Now, take a look at what happens when there is a common variable.
So basically at the end, all he did on that check was he just multiplied it back together just to make sure that it equals what it originally started at. So that's how I check it. Is first he factored out the 3, and then he put it back just to say we can double check by multiplying it back together. Okay, let's see example 2. I think we're going to do this on paper just to make it a little easier to understand than going through their 8 slides. Okay, so factoring this out, the greatest common factor, we kind of look at it separately. First, we just look at the numbers, right? So we have the numbers 6, 9, and 20, and we try to figure out, is there any number that all 3 of these have in common? Right, so this is 2 times 3, 3 times 3. So the only thing these 2 have in common is 3. But this is 4 times 5, and 4 is 2 times 2. So this doesn't have a 3 in it. It's only got 2s and 5s. This doesn't have 2s or 5s. So there's not a common number that we can break apart there. So we can't do anything with those. So those stay the same. But let's look at the variables. So here I'm going to write this a little differently. 6, A, B, 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 B. That's the same thing as this. I just wrote it A times A times A instead of A to the 3rd. And B times B times B times B instead of B to the 4th. Plus 9. And we got 6 A's and 3 B's plus 20 with 5 A's and 2 B's. Okay, so this is the same as what's above. I just wrote out the variables instead of doing them as the squared stuff. So now let's start with the A's. So this has 3 A's, which this also has 3 A's. It's got more than 3, but this one doesn't, so we can't pull out more than 3. And this one has 3 A's. So there are 3 A's in each of those terms. So we can pull that out to the front as a to the 3rd. Right? And that will factor out of each one of those. Now, what about the B's? There's 4 B's here, there's 3 B's here, there's 2 B's here. So this is the smallest amount. There's 2 B's. So we can take 2 B's out of that and 2 B's out of that. So we can factor 2 B's out of each of those terms and have a B squared. Which now, when we factor out 3 A's and 2 B's, what's left? We have 6B squared. That's all that's left in the first term. The second term, we got a 9, 3 A's, and 1 B. So 9A to the 3rd B. And then we have 20, 2 A's, and no B's at all. 20A squared. So that is the greatest common factor. This is factoring out the greatest common factor. 6 can look different than the B. A to the 3rd, B. That's all we could pull out because we couldn't pull out anything on the numbers. They don't have any common factor between 6, 9, and 20. But see, that's how that works. Now, if you can just look at this and tell, you don't have to write it out like this, but sometimes it helps if you're getting confused. Because we see there's an a to the third, there's an a to the sixth, so that's got an a to the third in it, and a to the fifth. So when we pull out a to the third, you just subtract. We pulled out 3 of them, so that leaves 3. We pulled out 3 of these 5, that leaves 2. Then we'll look at the b's, 4 b's, 3 b's, 2 b's. That's the smallest amount. So if we pull 2 out of each of those, that leaves 2 b's and leaves 1 b, and there's no b's down here now because we pulled them all out. They looked at the factors of 6, 9, and 20, right? And they found out that 2 and 3 is 6, 3 and 3, and 4 and 5, which is the same as 2 and 2 and 5, or 2 and 2 and 5. Nothing in common, so they left those alone. They did the factor tree: 2, 2, 5, 3, 3, 3, 2. Can't pull anything out. So they said, okay, now let's look at the A's and B's. And they did the same thing, pulling the A's and B's. I thought they put them in parentheses. I just put mine next to each other, but that's okay. 9 times 6 A's times 3 B's. So then they looked to say, we could pull out, and there you saw 3 A's, 3 A's, 3 A's, 2 B's, 2 B's, 2 B's. And they pulled it out in front and then rewrote it as a to the third b squared times 6b squared. That's what I did. Let's see, what else did they do? And then they checked it by multiplying them back together. So they multiplied this times the leftover polynomial and came back to the original. Oh, let's see. What are they doing at the end? They're comparing the exponents to the factor. So they're saying, yeah, when you had a to the fifth and you pulled out a to the third, that left a squared. And the b squared disappeared altogether because it got factored out. So that's what they're pointing out. So look for the smallest exponent from each term and variable. That's what you're factoring out. So if we had these two terms, 2x to the fifth y squared and 3x to the third y seventh, we cannot factor anything out of the numbers. 2 and 3 don't have any common factors. But there's x to the fifth and x to the third, so we can factor out x to the third. There's y squared and y to the seventh, so we can factor out y squared from both terms. So, all right, let's see what else they got here. Factor completely. 12vw to the fourth plus 28v to the third w to the sixth plus 4v to the seventh w to the eighth. So they're doing factor trees and all that kind of stuff. I'm going to write this one on paper. We'll do this one. Okay, so in this one we have 12, we have 28, and we have 4. So we can look at the factors of that. Can we factor any number that's in common with this? Well, this is 4 times 3. This is 4 times 7. And this is 4 times 1. So we can factor a 4 out. They all have 4 in common. So we can pull a 4 out front out of each term. Now let's look at the V's and the W's. This one just has 1 V. And this has a V, and they all have 1 V. So we can go ahead and pull 1 V out. Now what about the W's? Well, they all have W's. How many can we pull out? Look at that and think about that for a moment. We've got W to the fourth. This one has W to the sixth. This has W to the eighth. So how many W's can we factor out of each and every term? Well, you're limited by the smallest one. This one only has 4, so I can't pull out any more than that. But do they all have 4? Yes, this has more than 4. This has more than 4. So we can pull W to the fourth out of all 3 terms. So now we have to look what's left when we factor out 4 VW to the fourth from 12 VW to the fourth. Oh, the VW to the fourth are all factored out. And we factored 4 out, so that means there's a 3 left because it was 3 times 4. So that's the first term. There's no variables left because we were able to factor all of them out. 28, we factored out a 4, so that means 7 times 4 is 28. V to the third. We factored out one of those V's, so that leaves a V squared still left. We factored out 4 of the w's, so that leaves w squared. 4, 4, 4, that just leaves 1. We can put the 1. V, we pulled 1v out of v to the 7th, so that's a v to the 6th, which means we don't have to have the 1. It's coefficient of 1, but we can put it. W to the 8th, and we pulled out 4 of them. So this is what it factors down to. 4v to the w to the 4th, and then you got 3 plus 7v squared plus w squared plus v to the 6th, 4 to the 6th. Don't even have to put the 1 since the coefficient of 1 is not needed. And then to check that, you multiply those back to make sure you get this to this. So if you're not sure you got it, that's a good way to double check. Let's see what they did. They looked at the 12, 28, and 4, and they found, hey, we got a greatest common factor of 4. So they pulled a 4 out of everything. Then if they did it with a factor tree, if you like that better, this is 2 times 2 times 3. This is 2 times 2 times 7. This is 2 times 2. So since they all have a 2 times 2, that's 4. Factor it out that way. And then with the variables, you have v, w to the 4th. So they put the v's in red, the w's in blue to see how much each term has. They pulled out the v, w to the 4th, which we did as well. And they ended up with the 3 by itself, like we had, and then the 7 v squared, w squared, and the v6 w4. So that's the same thing we just did. And then they check it by multiplying it back together. You got to distribute it to all the terms, and it checks out because it's back what it was. All right, they got another one right here. I'm going to skip that one if you want to go through the 4th example because we got a lot to cover today. I'm not going to cover every example. Oh, this is what we want to look at. Difference of squares. We're looking at shortcuts. This is another cheat code. So let's look at a few things. First, how do we multiply 2 binomials together? You multiply the first term, the outside term, the inside. So you can use the FOIL method if that helps you remember it. When you have 2 binomials and you're going to multiply them together. So let's do a couple of examples like they're doing on there. So let's say we've got x plus 7 and x minus 7. So multiplying those together, if you use FOIL, you do the first ones together, then the outside ones. So that means that you take x times both terms. And then you go on the inside 7 times both terms. So x times x is x squared. X times negative 7 is negative 7x. So that's distributing that both times. Now we need to do the 7 both times. 7 times x is 7x. 7 times negative 7 is negative 49. Oh, look, these are like terms. Negative 7x, positive 7x. So this just equals x squared minus 49. Well, that was nice. Let's do this. 3, let's do b's this time. 3b plus 4 times 3b minus 4. Okay, first terms. 3b times 3b. 9b squared. 3b times negative 4. That's negative 12b. 4 times 3b is a positive 12b. And 4 times negative 4 is negative 16. Oh, look, those cancel each other out. Gives us 9b squared minus 16. Now, these are pretty cool. We only end up with a binomial on these that we're doing. So let's see what we have in common here. X squared, 49, 9b squared, 16. Let's just look at those terms. You notice anything in common about all of those? All of these are perfect squares. What do you mean perfect squares, Mr. Brock? It means like you could take the square root and it's a nice easy number. Perfect squares. These are all perfect squares. So by that, I mean that we can get this number by doing x times x. We can get this by 7 times 7. 9b squared is 3b times 3b. 16 is 4 times 4. They're all perfect squares. We can multiply something times itself to get each of these terms. Well, that kind of makes sense because if we go back and look at what we started with up here, we started with an x being multiplied by an x. And we had a 7 multiplied by a 7. And we had a 3b multiplied by a 3b and a 4 multiplied by a 4. And if you pay close attention, you'll notice that the only difference between the terms is one was positive, one was negative. One was positive, one was negative. And in each of those cases, we only ended up with two terms that were both squares, and there's a subtraction. There's a minus. We're finding the difference between them. There's something in math we call the difference of squares. And it's a cheat code for factoring. Difference of squares is a cheat code for factoring. If we have something that, let's say we take two squares. So I'm going to take x squared, and I'm going to take, well, let's do 9. 9's a square. And I'm going to take the difference. The difference. That means subtract. Difference means subtract. Right? Because if we add, it's the sum of squares. This is difference. Difference of squares. That means we can factor it using the cheat code that you factor the first one and factor the last one. X, X. That's a perfect square. So that's 3 times 3. And then you just make one positive and one negative. Oh, let's do that again. 4x squared minus, let's pick another square. Oh, let's do something interesting like 16y squared. These are both perfect squares because the first term is 2x. Because 2x times 2x is 4x squared. So that's a perfect square because I can multiply the same thing times itself. 16y squared is just 4y. 4y times 4y is 16 squared. And since there's a difference, we know one of these is positive and one's negative. Look, we factored that real easily. It didn't look real easy at the beginning, but it was real easy when we actually did it. So let's do 64x squared minus 81. Cheat code, we can factor that into two factors because it's a difference and these are perfect squares. Oh, let's make this even more interesting. Let's say this is to the 6th power. Well, 64 is 8 times 8. X to the 6th is x to the 3rd times x to the 3rd. So 8x third times 8x third equals 64x to the 6th. That is a perfect square. 9 times 9 is 81. So make one a plus, one a minus, and it's factored. Cheat code. So if you recognize that you only have two terms and that they're both squares, and you recognize, hey, this is the difference of squares, that tells you you can just quickly factor it. Quick, short factoring if you recognize that you have the difference of squares. Oh, that's pretty cool. But you have to be looking for it because it'll slip past you and you'll miss it. It's like you go all this work and you factor it and then you find out, oh, wait, that was just difference of squares. I could have just done that. So a binomial whose both terms are perfect squares and they're being subtracted is called a difference of squares, which means if it's a squared minus b squared, it's just a plus b, a plus b, a minus b. Just take the square roots of those two things. A squared minus b squared. And sometimes b squared looks like 4y. 4y squared is 16y squared. But you have to be able to recognize that, hey, these are both perfect squares. So I can just do one of them plus, one of them minus, and put their square roots. And when you multiply them back together to check, those middle terms are going to cancel out because you got a plus AB and a minus AB. So that's why you end up with just a squared minus b squared. Now this might be useful if you need a chart. If you know your multiplication tables, you don't need this. If you don't, here's some common numbers that you should recognize are perfect squares. Anytime you see those numbers, you should go, oh, are these both perfect squares? So, 1, 4, 9, 60. See, this is like 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 1, 4, 9, 16, 25. So hopefully you recognize these numbers. 121 you might not recognize. We don't get to 11 very often, but hopefully you recognize all those numbers immediately are perfect squares. Oh, that's perfect square. Let me see if the first term's a perfect square. Oh, it is. Great. I got difference of squares. Quick and easy. It's just being aware and recognizing it. So if you need this chart, put this in your notes if you need it. Hopefully you don't. Hopefully you got your multiplications down at least through 12. And you'll be able to recognize that quickly. Okay, here's a little test. Which of these are difference of squares and which of these they're just expressions. They're not difference of squares. So give me a thumbs up or a thumbs down if you want to use the little reactions button here. 81 minus 25t squared. Is this a difference of squares? Thumbs up, or it's not, thumbs down. 81 minus 25t squared. Oh, I see a lot of thumbs up. Everyone thinks so. Yeah, 25t squared is just 5t times 5t. 81 is 9 times 9. So we'll throw that in the difference of squares. How about this one? 64 plus 9r squared. Difference of squares, thumbs up? No? Oh, I'm seeing a little both. Need more opinions. 64 plus 9r squared. Oh, this is going both ways. I love it. Well, the first thing you're looking at, right, is you see the 64 is 8 times 8. 9r squared is 3r times 3r. But what's going on in the middle there? This is not a difference. This is a sum of squares. That's where we fooled you. We fooled you. You guys are trying to figure out if those are perfect squares, which they are. Both of them are perfect squares. Good job. But this is adding. It's not subtracting. It doesn't work with addition. It's only with subtracting. So that's just an expression. So you guys had a good eye for that. Good job. But yeah, remember, it has to be subtracting. So that can be the first thing you look at. If it's not subtracting, I don't even care if they're perfect squares. All right, 9g squared minus 12. Yes or no? Difference of squares, yes? No. Yes? No. Oh, I'm seeing no's. No. No. Well, 9g squared, that's just 3g times 3g. But we do run a problem in that 12, right? If you're not sure, you can go up here and say, Yeah, 12 is not, 9 is and 16 is, but 12 is not a perfect square. So that's just an expression because the 12 messes that up. How about 4t squared minus 49s squared? Thumbs up, thumbs down. Difference of squares, not a difference of squares. Daniel's going to go out there and say, yep. Luke agrees. Elijah's with it. Mary's with it. Maggie thinks so. Yep. I see lots of good job. That's 2t. Good job. And 7s. 2t and 7s. That is a difference of squares. How about 16h squared minus 1? 16h squared minus 1. Is that a difference of squares? Mary's going to jump out there and say, it is. Daniel agrees. Anyone else think it is or is not? All right. All right. Everyone thinks it is. 16h squared. That's 4h times 4h. So that's definitely a square. 1. Well, 1 is a square. It's 1 times 1. So yes, absolutely. That is a difference of squares. All right. Last one. 16y squared minus 4x. Oh, I've seen some thumbs down right off the bat. 16y squared minus 4x. Elijah says, no way, man. What's the problem? Well, the problem is the x, right? 16y squared, that's 4y times 4y. But the 4x, that's going to be like 2x times 2. There's not another x. So the 4x is not squared. If the x was squared, we'd be in good shape. But no, that's just an expression. All right, good job. Let's see. Here's a couple more examples on factoring. Factor completely 3d squared. Pardon me, 3d to the 4th power minus 363. Now, see, right away they put one that's off the charts, right? Not really. It's not off our chart because you look at this like this only goes to 144. Well, don't forget the first thing you would do is try to factor out greatest common factor. So you can divide 3 out of both terms and d squared out of both terms. Oh, tricky. Here, let's do that one on paper just so we have an example like that in our notes. Because we get so focused on difference of squares that we might forget that the first thing we should always do is check to see if there's a greatest common factor. Because we're like, oh, this is not a square, right? 3 is not a factor, so I can't use that. But wait a minute, this is divisible by 3. You can tell because 3 plus 6 is 9 plus 3 is 12, and 12 is divisible by 3. So that means this number is divisible by 3. So we can factor a 3 out of it. And there's a d to the 4th and a d squared. So we can factor a d squared out of it. So now 3d squared from 3d to the 4th, that just leaves d squared. 363 divided by 3 is 121. And d squared comes out of it. Well, now what do we have? We have 3d squared times. These are both perfect squares. So we factor it one step further, saying that I know these are both perfect squares. So this is d times d, and this is 11 times 11. So a plus and a minus. There it is, fully factored. So we used both things that we talked about, the greatest common factor and the difference in squares to factor that into these two binomials. So yeah, this was a difference of squares problem. We just had to factor out the greatest common factor first. So don't let it fool you. Don't let it trip you up. All right, I'm going to turn it over. I'm sure we've got some more fun stuff on the other side that we'll be doing here in just a minute. Let's see. So they went through their same steps, and they got 3d squared, d plus 11, d minus 11. And then they multiplied it back together just to make sure it got back to where it started. Here's another one, 4d to the 6 minus 1. There's not a greatest common factor because you have just the 1, right? But this is perfect squares. This is 2d to the third times 2d to the third, and this is just 1 times 1. So you can factor it to do 2d third plus 1, 2d to the third minus 1. Difference of squares. So just don't get fooled when they put these larger than squared. If that's an even number, it works. If it was to the 5th power, it wouldn't work, right? We couldn't do that. But since it's to an even number, we can split it evenly into d to the third, d to the third. All right, page 3. Perfect square trinomials. Now let's look at squared binomials and their corresponding products. All right, let's look at a couple of those. So that's what we'll do in our paper. So when it's talking about squared binomials, let's like taking x plus 3 squared. Or maybe we're going to do x minus 2 squared. We'll look at a couple of examples of squaring a binomial. And this is going to result in what we call a perfect square trinomial. Because the trinomial is going to be a perfect square because it's going to be x plus 3 times x plus 3. So let's do the math to see what this trinomial is going to look like. This is another shortcut. Once we recognize how this works, it's just harder to spot. All right, x times x, x squared, x times 3 is 3x, 3 times x is 3x, and 3 times 3 is 9. Oh, so look at our middle term. So we actually we have this 2 times 3x, because we have 3x twice, plus 9. And I wrote it that way for a reason. In its simplified form, it's x squared plus 6x plus 9, right? Because it was 3x twice. There's 3x twice. Over here, let's see, the x minus 2, this is x minus 2 times x minus 2. X times x is x squared, x times negative 2, negative 2x. Now let's distribute the negative 2 into both those terms. Negative 2 times x is negative 2x. Negative 2 times negative 2 is plus 4. So this really, since we have the middle term, is 2 times 2x plus 4, or x squared minus 4x plus 4. Now there's a pattern there. There's a pattern there. Let's say, let's break this down to where it was just a plus b squared, a plus b. What happened with that? Well, a plus b times a plus b is a squared plus ab plus ab plus b squared. As we distribute everything, a times a and a times b, b times a, b times b, you get this. So you get a squared plus 2 ab's plus b squared. Yeah, that's exactly what we got up here. If a was x and b was 3, and we said a squared would be x squared plus 2 times ab. Well, AB would be 3x, so 2 times that would be 6x, and then b squared would be 3 squared. Look, that's exactly what we got. There's a pattern. When you take a binomial and square it, there's a pattern. A plus b squared equals, you square the first term, you square the last term, You multiply the two terms together and double it. The only difference with this one, if you have A minus B, that's going to be A squared minus 2AB plus B squared. And this is, I guess I should write this in front of it to kind of clean that up. So this is A plus B squared. These are two patterns. If we can recognize this, make sure it's a B. A squared minus 2AB plus B squared. So let's say we have a problem like this. We've got x squared minus, let's say, 18x plus 81. X squared minus 18x plus 81. If we are paying attention and are quick to recognize, we'll say, hey, wait a minute. That is a perfect square trinomial. Because if we said A was X and B was 9, this fits the pattern of this. This is X minus 9 squared. Because I noticed that negative 9 times X is negative 9X. And if you double that, that's negative 18X. And this is X squared and this is negative 9 squared. So if you recognize negative 9x would double to be that, that's this pattern right here. It also helps the other way. What if I had, let's see, 2x plus 3 squared? Well, I could go through all the work, but I go, wait a minute, I can use this pattern. So this would be 4x squared. And this one, I just multiply them together and double it. So 6x would be 12x. And then I take the last one, plus 9. That's what that equals. Just following this pattern. This is A, this is B. The only difference is if this is a plus, then this is a plus. If this is a minus, then this is a minus. That's the only difference in there. You got to pay attention to what sign it is. If that is a minus, then you have a minus there. You still have a plus in the end. It's always a plus in the end. See how that works? This is called a perfect square trinomial because it's this binomial squared. Just like 9 is a perfect square because 3 is the factors. 4x squared plus 12x plus 9 is a square because it's 2x plus 3 squared. These are a little harder to recognize sometimes. Sometimes these are harder to recognize because we have to get used to looking for that pattern. These are a lot easier to recognize over here, right? X squared minus 9, difference of squares. Those are easier to recognize. These are harder to recognize, but they're a great shortcut. If you have these patterns written down in your notes and can look for those patterns, it can be very useful. Perfect square trinomials. So here's some other. G minus 3 squared. G squared minus 6G plus 9. See, it's the G is squared, the 3 is squared to be 9 on the end. And if you multiply negative 3 times G and double it, you get the negative 6. You see that patterns there. The 4G plus 11. 4G times 4G is 16G squared, so that goes in the front. 11 times 11 is 121. It goes in the back. And the middle is multiplying the two terms together and doubling it because there's two of them. There's a 44G and a 44G, so you end up with the 88G. That's why we double it, because that middle term appears twice. So All perfect squares. Yeah, if you see that the first term and the last term are perfect squares, that's when you want to look and say, oh, wait a minute, maybe this is one of those things. If the first term and the last term are not perfect squares, it's not going to be a perfect square trinomial. There's no chance. So that's the first thing you have to see, is that the first term, like g squared and 36, both have to be perfect squares. Then you're like, oh, there's a chance. So you have to take the square roots of both of those. That'd be g and that'd be 6. So 6g doubled would be 12g. So that is a perfect square trinomial. They're all perfect squares. The last terms, all perfect squares. The middle terms, if you take the square root of the first and last and double them after you multiply them together, you get to the middle term. And then the signs of the first and last terms are all positive. It's always positive at the beginning. Like the G is always positive. The 4G is always positive. On this, it's always positive for the first term and the last term. It's just the middle term that can change. So it's the middle term is going to be equal to whether it's a plus or a minus. Now it says work backwards. G squared minus 16g plus 64. So that's a G and an 8. So, and this is 8g doubled, and it's a negative. So this must be g minus 8 times g minus 8, or g minus 8 squared. You basically cut that in half to find the factors. If it's negative 16g, you know it's a negative, and it's 8g because you cut it in half. Here's those patterns that I had written down on paper. A squared plus 2ab plus b squared is a plus b squared, or if it's minus, it's minus b squared. So here's another one for us to identify. Is this a perfect square trinomial? 6a squared plus 12. Well, this one we can say no immediately because 12 is not a perfect square. We don't have to try to calculate the middle number. Since 12 is not a perfect square, that's not a perfect square trinomial. We know that already. How about this one? 144r squared. Is that a perfect square? Yeah, that's 12r, right? 12r times 12r. And 1 times 1. So what's 1 times 12r? That's 12r. And if we double it, that's 24r. That's a perfect square. See, 5g and 7. 5g and 7 multiplied together would be 35g. If we double that, it's 70g. 4p and 9. Oh, look, there's a negative on the last term. We don't even have to check it. Can't be a negative on the last term. That has to be a positive. This one's a positive and a positive. So this is 11s and 5. 5 times 11 is 55. That's half of 110. Let's see, x and 4. That's 4x. That's not doubled. It's not. All right, let's try one more example here. All right, hopefully you can see that because our paper's getting a little purple from the other side. 32d to the 5th minus 16d to the 4th plus 2d to the 3rd. We want to factor this. First thing you're looking at is like, well, this is not a perfect square. That's not a perfect square. This must not be a perfect square trinomial. But did you forget the first step? First step, always. Greatest common factor. Always, always, always look to see if there's a greatest common factor. So we've got 32, we've got 16, and we've got 2. All of those have a 2 in it. So we can factor out a 2. We got a d to the 5th, a d to the 4th, and a d to the 3rd. So we can factor out d to the 3rd from every term. Now let's see what's left. If we pull 2d to the 3rd out of 32, d to the 5th, 32 divided by 2 is 16. D to the 5th divided by d to the 3rd is d squared. That's a perfect square. So now it's looking closer. Let's factor out continuing. Negative 16 minus 2 is now negative 8. D to the 4th, factor out d to the 3rd. There's just a d. Our last term, 2d to the third. We factored out 2d to the third, so that's just plus 1. Remember, we have to divide it out. We don't subtract it out. We're dividing this by this, and it's just 1. 1 is a perfect square. 16d squared is a perfect square. This is 4d times 4d. This is 1 times 1. So 4d times 1 is 4d. Double it, and it's 8. This is a negative. This is negative. So this is, let's see, we still have 2d to the third. This is going to be 4d minus 1 squared. That's it. Which is the same thing, remember, as 4d minus 1 times 4d minus 1. Because it's squared. So there's 2 factors of this. There's 2 factors of this. Either one of these are fine. Fully factored. Do not forget greatest common factor. That changes the whole problem because this did not look factorable until we realized, oh, wait a minute, we can factor 2d3 out of every term. Now it looks factorable. All right, we're going to need a new sheet of paper because we're not even to the second lesson yet. Let's see what's left here. This is the last page right here. In this section, you'll take information learned on factoring products one step further. So let's try this in t to the 8th minus 81. Okay, this is taking everything we know and factor it together. There's no greatest common factor. That we see right away. Are you going to focus? There we go. But these are both perfect squares, right? So this is difference of squares. See, it's a difference. We're subtracting. So this is t to the 4th plus 9 and t to the 4th minus 9. Difference of squares. Make sure it looks like a 9. Difference of squares. We're like, yay, we factored it. Well, yeah, but this is a difference of squares. T to the 4th and 9. So this is t to the 4th plus 9, which sum of squares, there's no shortcut. There's no way to factor that. This is done. This is prime. But this is t squared plus 3 and t squared minus 3. Hey, this is a difference. Well, that's not a square. T squared is a square. 3 is not a perfect square. That's as far as we can factor that. But don't factor it once and stop there. You need to look and see, can I factor it further? Yes, in this case you can, because this can factor to this. That's the problem we run into sometimes on these problems, is you stop too early. It's like, oh, it factors further than that. But now we got a difference. We have a sum of squares. We have t squared plus, that's a sum of that. And this is not perfect squares. So that's about as far as I can go. I don't think they took it any further than that themselves. See, they did t to the 4th plus 9, t to the 4th minus 9. And then, so there's what it factored down. T to the 4th plus 9, t squared plus 3, and t squared minus 3. That's it. That's the factors. What did they do on this one? They did d squared minus 8d squared plus 16, d to the 4th, I mean. So that is d squared, and this is 4. This is a perfect square trinomial. So they factored it to d squared minus 4, d squared minus 4, but those are difference of squares. So then they had to go further by d plus 4, d minus 2, and d plus 2 minus 2 twice. So it factors to that. All right, that's the lesson summary. It's like, wow, we're on page 4 of 9, and that's a lesson summary. Yes, that means 4 pages of practice problems. So this goes over the greatest common factor. Make sure you pull the greatest common factor out. The difference of squares. binomials, when to recognize that, the perfect square trinomials, the patterns for that. And then check to see if it can be factored further. Don't stop with the first factoring. T to the eighth minus 81. It factors again. All right, there are 4 pages of practice problems. I'm not going to go through those. We've already used up an hour of our hour and a half time. But you can match these. This is the greatest common factor thing. When you pull out the greatest common factor, what matches? 3 activities there. There's more practice problems here. Factor completely. All right. More problems over here. More practice for factoring. What is that? More problems over here. Like I say, there are 4 pages of practice problems. This has 10 problems right there. And then we have the assignment. Let's look at the assignment while we're here. Factor completely. All right. Looks like you can only take a greatest common factor out. Didn't factor any farther. This one, factor completely. Which one of those 4? Oh, this one, which of the following is a factor? So this one you factor as far as you can get and then figure out which one of those that would be. One of the factors of this one would be one of those. So factor that. Factor this one completely. Oh, we got 10 problems. Factor. So these got to factor and then choose which is the correct set of factors. Factor completely. Oh, this is great. One of the factors of this one is it 8x, x plus 10, x minus 10, or all of the above? That might be all the factors. So you got to figure out, is it all of them? Is it one of them? Maybe it's not x plus 10 and x minus 10. It's only 8x, and the other factors are something different. So you got to figure out what you're going to answer on that. And this one's the same way. Factor this as far as you can get it and tell me, is there just one of the factors listed, or is that all of them? And what is the completely factored form of t to the 4th minus 16? 10 great factoring problems there. Yeah, well, wait. Let's look at our next lesson. Factoring by grouping. This is quadratics right here. So methods of factoring. The discriminant and the roots. Now, fortunately, we've got some experience with the discriminant. We had that with our systems of equations. So the skills of factoring trinomials is like a tree. There's a couple of branches, like finding the greatest common factor, special products, that work in special cases, right? Difference of squares, we did that, special cases. But the trunk of the tree holds it all together and leads to what types to expect. So this is called the discriminant. The discriminant, we're going to look at that again. Remember, we can only use the discriminant when we have a quadratic equation, ax squared plus bx plus c. And the discriminant is that b squared minus 4ac. So let's review that with this sample problem they gave us. Okay, so this is in the form ax squared plus bx plus c. So we care about the a, b, and c because the discriminant is b squared minus 4ac. All right, that's the discriminant. Oh, I just got room to squeeze it on there. That's the discriminant. B squared minus 4ac. So let's take these numbers, a, b, and c, a, b, c, and calculate the discriminant. So b squared, 7 squared minus 4 times 2 times 6. So that's 49 minus 2 times 4. 4 times 2 is 8, times 6 is 48. So it equals 1. Is this a perfect square? Yes. Yes. If perfect square, it's factorable. That means we can factor it because it's going to have 2 rational solutions. Okay. If not perfect square, then use the quadratic formula because it has two irrational solutions. If 0, right, because it could equal 0, one solution, which means it's probably a perfect square trinomial. Yeah, the discriminant 0, it's a perfect square trinomial if it's 0, because that means it's going to be x plus 4 squared. It's going to have the same solution twice. Trinomial. Ooh. Perfect square trinomial. And if negative, then two complex solutions, which means imaginary, which means use quadratic formula. So that's what the discriminant's good for. All those situations. We can check to see what is it. Is it a perfect square? Then we can factor that equation. If it's not a perfect square, then but it's positive, then we can use the quadratic formula. It's going to be two irrational solutions. Maybe it's going to be 2 plus the square root of 5 or something like that, right? But it'll be a real number, just not an integer. If it's 0, there's just one solution. It's a perfect square trinomial. That means it's going to be like x minus 2 times x minus 2. You'll have the same solution twice. If it's negative, that means it's imaginary. Two complex solutions, and you need to use the quadratic formula because you're going to end up with like 3 minus the square root of negative 5 over 2 or something, something weird. All right. So, yeah, that discriminant that we were talking about back with systems of equations helps anytime that we have a quadratic to tell us what we're looking for. So, let's not forget our friend, the discriminant. The friend, the discriminant, the b squared minus 4ac. Guess I should just highlight that. B squared minus 4ac. That's our friend, the discriminant. Page 2. This has 10 pages on this lesson. Factoring by grouping. Watch the following pair of binomials being multiplied. Okay, t plus 3 times t plus 11. T times t is t squared. T times 11 is 11t. 3 times t is 3t. 3 times 11 is 33. Okay, so we see how we ended up there? Now let's look at another one. Oh, wait. They simplify it. They got to put the 11t and 3t together. So we got t squared plus 14t plus 33. Now look at this one. T plus 3, s plus 11. We changed it from t to s. So t times s is st. You generally put them in alphabetical order. St plus 11t. That didn't change. And 3 times s is 3s. And 3 times 11 is 33. That's simplified as far as it can get. St plus 11t plus 3s plus 33. Okay, that's a little different when one's t and the other one's s. So what is the difference of the outcomes? Well, in the first group, the middle terms combined because they were both t's. It was 3t and 11t. But in the second one, they couldn't be combined. We had 4 terms left at the end because there's nothing that's like terms. So using what you saw in group 2, let's try working backwards to find 2 sets of binomials that multiply to produce x squared plus xy minus 2x minus 2y. All right, let me write that down. But that's kind of what we ended up with. We said t's and s's. So to figure this out, let's take the first 2 terms and group them together because they have something in common, right? They both have an x that we can factor out. X squared divided by x is just x. Xy divided by x is just y. So we have the same thing we can factor out. So that means the rest of it, we can also factor something similar out. We got a negative 2x and a negative 2y. So if we factor negative 2 out, negative 2x divided by negative 2 is just x. Negative 2y divided by negative 2 is just a y. Now I've got two terms. I've got this term, x times x plus y, and negative 2 times x plus y, which means both of these have the same thing that can be factored out. Just like I factored out up here, the greatest common factor, both of these have an x plus y, so I'm going to factor it out, which if I factor x plus y out of this, that just leaves x. I factor x plus y out of this, that just leaves negative 2. And these are the two factors that end up with that. Let's test that. X times x is x squared. X times negative 2 is negative 2x. X times y is xy. And y times negative 2 is negative 2y. Look, it's the same thing. They've just been put in a different order. The negative 2x is over here and the plus xy. We could rearrange that real easily, and we get the exact same thing. So we worked backwards to figure out what were the factors, and we did it by breaking them into groups of similar terms. So factoring the whole thing, look at the x plus xy plus the x. Negative 2 could be factored out of the second two terms. Now they both have an xy that we can factor out, and you end up with the x minus 2 and x plus y. That's called factoring by grouping. Let's see, how long is this video? 3 minutes. Okay, we got time for a 3-minute video.
Check each term in the original polynomial for a greatest common factor before trying to factor it any further. The first term has a coefficient of 1, so this polynomial does not have a numerical GCF greater than 1. The last term doesn't have any variables, so a variable cannot be factored from each term. Therefore, a GCF will not be factored. When factoring by grouping, look at the expression in pieces to make it easier to find the common binomials hidden within. Group the 4 terms into pairs, the first 2 terms and the last 2 terms. The next step is to factor the GCF from each group. First, factor the GCF from the first pair of terms. C squared d and negative 4cd have 1c and 1d in common, so the greatest common factor is cd. When cd is factored out, you're left with c minus 4. Now, factor the GCF from the second pair of terms. 4c and negative 16 have a GCF of 4. When 4 is factored out, you're left with c minus 4. You're finished with this step. The next step is to factor the common binomial from each group. Notice that the binomials in parentheses are exactly the same. c minus 4 is common to both terms. Therefore, it is a GCF, which may be factored from each term, leaving the other factor, cd plus 4. So the final factored solution is c minus 4 times cd plus 4, but you're not quite done yet. Don't forget to check the factors by distributing. If the product of these factors matches the original polynomial, they are correct. C times cd is c squared d. C times positive 4 is positive 4c. Negative 4 times cd is negative 4cd. And negative 4 times positive 4 is negative 16. You can see that the terms of the product are not in the same order as the original polynomial. But these terms can be rearranged. Just don't forget to take the sign with each term, and that's it.
And that's it, just like the one we did. I want to do just another problem or two just to illustrate where you might make a mistake. Because I know this factoring by grouping you've seen in Algebra 1 some, and some of you like to factor that way, and some of you like to do other things, but I want to talk about factoring false primes. So let me write this problem down. Could be that you start working this one. You're like, okay, I can factor by grouping. So let's factor by grouping. Group these two together. And you might say, okay, y can come out of both terms, which leaves us with an x plus 4. And then you might say, well, I got 5 and 20. What's up, Luke? Oh, it didn't switch, did it? Thank you. Thanks for catching me there. Wonderful. All right, so 4x plus 4y. We group those, and we can pull a y out, which leaves x plus 4, because we pulled a y out of both terms. And then we look at this, and we got 5 and 20. You might say, well, I can pull out a 5, and that leaves negative x minus 4. That will get where you're like, wait a minute, there's nothing in common. This is x plus 4, and this is negative x minus 4. That's an error in solving it, because what you should have done, you're trying to get an exact same term. I can get that term if I pull out a negative 5. Negative 5x divided by negative 5 is a positive x. Negative 20 divided by negative 5 is a positive 4. And now I've got x plus 4. And I can factor that x plus 4 out, leaving y minus 5. So that's something to watch for. Sometimes you need to pull the negative value out so that you can get the same terms, because you need to have the same binomial on both of them. So pay attention to what sign you need to pull out to make that happen. Pull out negative 5 instead of 5. Pull out negative 5 instead of 5. That's the main point there. Okay, let me look at the other problem real quick, because this is probably even more common that we mess up. Okay, so we might look at this one. We said, okay, we want to factor this by grouping. And so you go, all right, nothing. I can factor out a 1. And if I look at the second group, I can factor out a 1. So you factored out nothing, right? Because I just factored out a 1, nothing changed. Sometimes when you write this down, you're writing them down, you need to rearrange it. And we can rearrange this, and it'll work. If we swap these two terms, let's just trade places and rewrite the problem. So xy plus 4y minus 20 minus 5x. Now try grouping those. Or maybe even I'm going to put the x first. Let's swap these as well, just so it'll be in the same order. So I can say negative 5x minus 20. Now, do we agree these are still the same equation? I have not changed anything, right? I've just rearranged them. But 2 plus 3 is the same as 3 plus 2, right? I can rearrange things as long as I'm still subtracting the 5x, I'm still subtracting the 20, I'm still adding the 4y. I didn't change the signs, so this is exactly the same equation this and this. I've just rearranged what it looks like. But now if I group them, xy plus 4y, y comes out, and I've got x plus 4, negative 5x minus 20. If I pull negative 5 out of that, x plus 4. See, now I've got the x plus 4, y minus 5. See, this is the same equation that we just did up here, but when it gets rearranged and you look at it wrong, you're like, wait a minute, there's nothing to factor. Sometimes you need to rearrange. We just rearrange to make it work, because that's where we'll fall into a trap sometimes. We'll look at it and think, oh, I can't get any way to factor that. Yes, you can. You just need to rearrange the terms, put them in a different order, which doesn't create a problem when you're adding and subtracting. As long as you keep the signs and make sure you're still subtracting what you're subtracting to start with. So that is under the false primes. You may think, oh, there's no factors. This is a prime polynomial. There's no factors. Yeah, there are factors. If you rearrange it, you can pull the factors out. So the y minus 5x plus 4. So that's a little nice thing to worry about. If there are truly no factors, like on this one, let's see. There's not a common factor, so they can't pull out a greatest common factor. Here they group the terms, and you factor the greatest from each one. What did they end up with? Did they pull something out of this one? CDD plus 7D. They was able to pull out a D. The second one, they pulled out an 8. And that left D times CD plus 7 and 8 times C minus 2. There's not a common factor. See, CD plus 7 is not the same as C minus 2. So this was a prime polynomial. There really aren't any factors to pull out of it. I mean, it looks different because they pulled D out of 2 of the terms and pulled 8 out of 2 different terms, but there wasn't anything that they could factor out of the entire equation. And sometimes that happens because there are no factors. It's a prime polynomial. But don't make the mistake of thinking it's prime when you could have rearranged it and factored it. Factor trinomials by grouping. So they multiply these two together. What time is it? We're about out of time here. But there's a couple of examples in there. The lesson summary is right here. But again, it's just factoring by grouping. This is where they checked the discriminant and found out that, hey, it's a 49, so it is a perfect square. So this will lead you through the process. 6 squared minus 11x plus 3. You can factor that. You can use a quadratic formula if you need to. All right, but you can always use that discriminant to tell if factoring is best or if I need to use the quadratic formula. Factor the greatest common factor when possible. And this one's a prime. There wasn't any factoring to do. Lesson summary. Starts out with the discriminant because that tells you there's one solution, 2 rational solutions, 2 irrational solutions, or 2 imaginary solutions. Here's the steps. Oh, this is great to have in your notes. First, factor the greatest common factor. Then group your terms. If you have 4, this is for factoring polynomials with 4 terms. Get the greatest common factor from each of the groups of 2, and then factor out the common binomial to figure out. Steps for factoring trinomials by grouping, factor the greatest common factor. Sometimes you have to split the middle term yourself, which that's how you learn it in Algebra 1, and then we can group it. But we are out of time. It is the end of class. So if anyone struggles with any of this, let's look at the assignment real quick. Please come email me or something. We'll find some time since there's no other A days this week. Starts out, what is the value of the discriminant? You just have to calculate the discriminant. This one, predict what type of solutions you're going to get. 2 rational, 1 rational, 2 irrational, 2 imaginary, which just means calculate the discriminant. Select one of the factors of this. Select one of the factors of this, one of the factors of this. All right, that's what you have. 5 problems on the second assignment there. Whew, man, we were running hard. Anybody else sweating? Wow, we got through it all, though. But you've probably done factoring by grouping before, but we probably looked at it a little bit differently today with a few other things. So if you struggle with any of that, please get with me. I'm happy to go over it with you again on any specific problems you're struggling with and see where your error is coming at, and we'll get it worked out. But Otherwise, guess I won't see you guys till next week since it's B-Day Friday. So have a super week, and we'll see you Halloween week. Wow, that's next week. See ya.